Alrighty, so here we are again with even more quantum mechanics. And this time we're going to talk about imaginary numbers because last time I mentioned them and I said I was going to explain what they're even doing here. And, if you've never learned that much about imaginary numbers, you might be surprised to see what use they can be, um, and why they're here. And you might learn a lot about imaginary numbers that you never learned before. But let's get to it. So first, we'll talk about some superposition of, real and imaginary components. Then, like, why it's here for the main reason, and then there'll be trivia with Fourier transforms. Um, anyway, let's get to it. So let's see here. Superposition. So what superposition mean? Oh, that is not the right pixel size. Superposition is a word that you might hear about quantum mechanics a lot. But what does it mean? Well, consider something like it's basically like another word for what we call a linear combination. Sometimes, sort of, but not quite. I'm going to give you an example of this. Suppose we have a vector. You may have seen this before. It will have components of the x vector and the y vector. We say that this vector then is a superposition of this component and this component, or a combination. Another example of superposition is like, suppose you have a giant block and you have some people trying to move it. As you can see here, we have this vector, and this vector with a superposition. Would be to just make a giant vector that's like all of them put into one. And so, that's just a fancy word. Anyway, now we actually have to get on to imaginary numbers. Then we'll start with a slightly familiar concept, but I'm going to color code some of this. Let's take this vertical axis and this horizontal axis. And we're going to do something special with this. We'll take this green component and we'll draw a circle with this. Like that, and then like that, and then like that, and like that. And we'll say this is like some thing that can oscillate back and forth. And it's, we have some angle, which we'll call theta. Now, let's say that this is like a ball and it goes around the circle. How do we compose the motion of the ball? Well, we can actually do this relatively easily. So we have to break it up into a superposition of its vertical and horizontal components. And we'll do that now. Say like it starts here, for example. It will go here in this direction, and then it'll go this direction all the way into the left when it reaches its furthest leftward point. Then it will go this way back and then back again until it reaches its starting point horizontally, and then back and back again. And if you might know anything, you might think this is a bit like a cosine wave. Because if you may recall, cosine of theta looks a little bit like this. If we have, this is the graph it'll start off here. That'll go down and up, down and up as theta progresses. And we're going to do exactly that. But we're going to rotate it. We're going to put it over here. So we'll have this horizontal axis, and this bit here, we're just going to call it theta. And so it'll go like this, this, and so on. I will take this as the horizontal component. Is equal to cosine of theta. Now onto the the vertical component. Well, it'll start at 0, then it'll go up, reach its maximum height, go down, back to 0, and then down again, back to the bottom, then go up again, and up again, back to the top. And this, you might recall, is a bit like a sine wave. So we'll draw that here too. We'll draw this and this, where this is theta. And, it'll look a little bit like this. And so the vertical component is equal to sine of theta. Now, you might think, wait, back up. How would we model this behavior? Because we have to combine this vertical and horizontal components together to get a singular equation. You might think, oh, well, we can just take, cosine theta and we'll just add sine theta. But this isn't quite right, because these can combine together to create a singular wave, which isn't really what we want, because these are separate. These are two very different things, because this is horizontal, this is vertical, and we have to make sure that they cannot directly combine. And so this actually has a very easy fix that a man named Euler discovered a long time ago. All you have to do is multiply the sine bit times I. And now you can't combine them, because, this bit, this horizontal bit is real. And this vertical bit is imaginary, and so they stay separate. One way of thinking about this now is that this sideways component, we'll call it the real number line, which is all the numbers from like 0, 10, -5. And this has the imaginary bit, and the imaginary unit in this case acts a bit like a y-axis, and it helps us track both the vertical and horizontal components of the oscillation. And this is important for, wheels, but also things like sound waves and such. And that's why it's superposition, because it's a combination of the real bit, cosine, and the imaginary bit, sine, and together this gives us the complete circular motion of the thing, both vertically and horizontally. Now, on to, this stuff is very good. Now, why is this in quantum mechanics? It's very cool, but why is this here? Well, we model this using Euler's number, which is E. That's right, that's where the E comes from. But we're going to label it E to the I times theta. And keeping this property in mind. In fact, I am going to put this up in the corner where we can remember it. because it's going to be nice to have later. E to the I theta is cosine theta plus I times sine theta. And as theta progresses from 0 degrees to 360 degrees, it oscillates around and around. You might ask why is this important? Well, this is important because there's something called the heat equation. Hang on. Which makes use of something like e to the negative k times t, where k is some variable, and because you're wondering this, this is our t, and this is the temperature. This block here will look a little bit like this. Essentially, as t progresses, the temperature goes down, because if you can imagine something like an ice cube, and we'll see how well I can draw ice cubes. Now, as time progresses, heat will leave this thing. It might be worth noting, seeing also the derivative right now. You may remember the property, but just to remind you, the derivative of e to the negative k t with respect to t is just equal to negative k. I'm going to have a different color for this. Negative k times e to the negative k t. So if we have our graph of temperature over time, the derivative looks a little bit like this. And as you can, which makes sense, because as our ice cube, emits heat, or absorbs heat, really, it's not emitting heat, sorry. It's slowly matching its temperature to the surrounding air. And obviously this means that the temperature, the rate of change of temperature, which is, this bit here, and sometimes this bit here, it approaches 0, and it's great for modeling heat because as time goes on, the amount of temperature entering, say, an ice cube or leaving, say, a hot stove will decrease as energy goes out into the environment. But this is not good for a quantum particle, because if psi is like either of these, then that means as like time progresses, the probability of finding something like an electron goes down to 0, and that won't do. So instead of doing e to something t, we simply fix it by doing e to the I times t, and a negative. This means that instead of going down to 0, it will instead oscillate. It'll go around and around and around like we saw earlier with cosine and sine. And so it won't go to 0. It'll just stay consistent. And this is why imaginary numbers are everywhere, all over the place in quantum mechanics, including wave mechanics. Like the time dependent, if you include time, I think it's like, I better look it up. Give me a quick second, because I have to make sure I'm getting the right equation. Time dependent Schrodinger equation. Let's see. Yeah, it's I times h bar times d of psi with respect to x and t with respect to t, which is equal to the energy, which is like earlier So, hang on. Negative h bar squared over 2m times del squared plus v of all that times psi. Oh, and in case you didn't know, this bit is a derivative as well. It's just a shorthand for writing space derivatives. Anyway, as you can see, we have an imaginary number here, and that's because when we don't include time, there won't always be an imaginary number in our wave function, but if we do include time, there will usually be imaginary numbers, and that's to enable the wave function to oscillate rather than just go to zero, because you might recall this bit is related to the energy of the particle. If we recall that the energy of psi is equal to like the second derivative, well, actually, this bit of negative h bar squared over 2m times the second derivative of psi with x plus v psi. Energy of psi always has to stay non-zero. It can't go to zero. If I hold on to an electron, it's not like the energy is going to go to zero and the electron will just vanish into thin air. That doesn't work. So in order to make this quantum mechanics work, we have to include the imaginary numbers so that we can use the e to the I theta, so that way it doesn't decay. And another example that we will use is the Fourier transform, which will kind of combine a lot of the calculus we've learned so far. Now, mostly we've dealt with wave functions that have to do with space, but sometimes we can have wave functions that deal with time. We can have, let's say we have phi of k. Oh, that's not a k. Oops. K. And it's equal to something, whatever, blah, 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 blah. Doesn't really matter what it is. And let's say that this is related to momentum or something, some component of the quantum particle at some instant in time. Let's say t is equal to 2 or whatever. It doesn't really matter because in this case, there is no time variable. And for reference, this k variable basically has to do with how much energy is in the system. Don't worry about this too much. This is just momentum wave function. And let's say that we want to turn our momentum wave function into a full, complete wave function with space and time included. We have to include space, we have to include time. Hang on. I have flicked my notes. Let's say that, we want to turn it into this. Well, this is like momentum. There's actually a simple, simple, it doesn't look simple. If we take the integral of phi of k and multiply it by e to the I, say negative I times k of x, and take the integral with respect to wrong variable k, this will give us our wave function. As you can see, this includes the psi, the integral bit, and it includes the imaginary number bit. And this is what enables us to convert the momentum into position and time. It's like the wavy version of Heisenberg, where delta x, delta p, then equal to like h bar over 2. You might remember that. This is like the whole thing. And you can see why I had to learn some calculus, because this includes a lot of stuff that we learned lately. Let me think. Don't really much to these imaginary numbers. All you have to know is that they handle oscillations in the quantum system, and without them, the math wouldn't really model the particles very well. And, well, there's not really anything much more to this calculus mechanics yet. Next time, we'll actually be going into a completely different mathematical bit of quantum called hang on. Those letters are not thick enough. Linear algebra. And linear algebra, I know it has the word algebra in it and linear in it, and so it sounds like it's something you would learn in kindergarten, but trust me, it's not, as we'll find out next time. But for now, we probably have enough to chew on for a moment with imaginary numbers and integrals and complex conjugates and derivatives and e to the x and e to the t. And so I'm going to leave it off for now, and hopefully this wasn't too confusing, because imaginary numbers can be confusing for some people. Anyway, next time we'll be starting on linear algebra.